Okay, so off we go. Here's where we were last time. We had been talking about change of variables, and I'm sure you've noticed by now there's a lot going on with change of variables, right? There's a lot to keep track of, lots of different versions of it, different ways to apply it depending on the situation. So that's why, as I mentioned at the time, I didn't want to go into the origin of the stretching factor formula. We had enough going on to keep track of at the time. So now that we've got a few examples under our belt, hopefully you see how change of variables kind of mechanics, kind of how it works. Let's talk about where that formula comes from. So do keep in mind that what the stretching factor is the thing that you multiply by a little piece of input area to get a little piece of output area. And as you see, I've set this up as looking at a little rectangle in the pullback domain and its image. Now you got to keep in mind this is at the small differential scale, and so we expect that this would be approximately a parallelogram. Not exactly, a little curvature maybe, but well approximated by this parallelogram. Okay, so I'm looking for the factor that we multiply by the green area to get the blue area, pretty much. Okay, so I'm going to start by thinking about the edge vectors, and I think it's a fairly easy pitch. That first edge vector is in the E1 direction, and its length is du, representing the width of that little rectangular box there, and so du. So that vector is E1 du. And now I ask, rhetorically, what do we do to input vectors to get output vectors? And the answer is you multiply by the derivative matrix. The derivative matrix is the thing that turns input vectors into output vectors, right? So input vector times derivative matrix gives you that output vector. Okay, likewise for the second edge. Okay, next. How do I compute an area? How do I compute an area here of a parallelogram? And importantly, this is a parallelogram in 2 dimensions, not 3. 2 dimensions. Old formula from Chapter 1 or Math219, depending. The area of a parallelogram is the absolute value of the determinant of the matrix whose columns are the edge vectors. That's our old formula from way back when. Okay, fine, what can I do with that? Well, you take this great big monstrous expression here and you can simplify it in a couple of different ways. One thing you can do is note that scalars will factor out. That du right there, that's a scalar. Scalars in a column factor out of determinants. And likewise, this one factors out as well. And then that leaves us just with this matrix to try to understand. And what can we say about this matrix? And there's different ways that you can come at this. But that matrix I like to observe as being dg times the matrix whose columns are E1 and E2. Now that's just a reference to how you do matrix multiplications. And in some sense, one column at a time. Flashback to linear algebra, see this however you prefer of several options. And then I make the observation that, check it out. This matrix right here, I wanted the highlighter. This matrix right here, the columns are E1 and E2. That is literally the identity matrix, and anything times the identity matrix is itself. Right, so this whole great big horrifying looking formula that I had here in green is just dg, as it turns out, right? So really nice little punchline. Okay, so who cares? What does this have to do with the stretching factor? And I'll just remind you real quick that our big goal was to compute this area, which I have, as being some factor times this area, which I have. And that factor, the thing that I multiply by green to get blue, is, as promised, the absolute value of the determinant of the derivative matrix. So there you go. That's why the stretching factor is what it is. And ultimately not that bad of a calculation, but you got to set it up just so. Okay. All right. So last thing we'll say about this before we move on to the next big topic. What do you do in 3 dimensions? And the punchline is basically, approximately, it's exactly the same. Right? So if you have some undesirable domain in the target, and by the way, oh my gosh, is that undesirable? Now think about how you'd slice that up. You hit just a load of corners, right? And you side swipe a load of faces. The cross section is going to be all kinds of weird. You'll be hitting corners as you slice those up. This is a nightmare. Okay? Okay, so that being the domain for some integral that I need to compute, we're going to view it as being an image with the idea in mind that I can then do a pullback, just like with the 2-dimensional case. The whole hope is that this blue undesirable domain is the image of something nicer, which will then be the domain for my new integral. Much better, right? Rectangular box, of course, is the dream if you're doing triple integrals. That's the world's best domain for a triple integral. And a certain amount of it is just plugging in. After all, x, y, z is literally g of u, v, w. That's what g does. It takes u, v, w as inputs, x, y, z as outputs. And the only thing we got to figure out to make this all legal is what's the stretching factor. And so what is it then that represents a little piece of volume on the right? And in particular, how can I view that as being a factor times little pieces of volume on the left? And the answer, just like before, is the absolute value of the, I like to call this the Jacobian determinant. I find it flows off the tongue a little bit better than determinant of the derivative matrix. So anyway, but same formula as it turns out. Now that's an exercise for y'all to fill in the blanks on yourself, and we just talked through how you're going to go about doing it. You're going to copycat exactly this argument right here. This is a wonderful little exercise. The only difference is that instead of having a little 2-dimensional rectangle, you're going to have a 3-dimensional rectangular box. And instead of having as your output volume a 2-dimensional parallelogram, you're going to have a 3-dimensional parallelepiped. But it's still edge vectors. They're still related by the derivative matrix. You're computing volume, which will again still be an absolute value of a determinant. It goes through in almost exactly the same way, different details, morally equivalent. So that is a really good exercise. I hope you'll give it a shot. And again, this is the answer. And by the way, notice we use this same little convenient shorthand for how to represent that stretching factor. Yeah.
Sorry if this is obvious, but is the determinant of the Jacobian derivative, is that the scaling factor?
Yeah. That is what I meant to say here. Yeah, this what I have in purple is the stretching factor. That totally. Yep. Exactly. All right, so we're going to make use of this in the next example. In preparation, though, for that example, there is a quick little theorem I want to just get on the board. It's very convenient. It comes up. Not rare. Not rare. Kind of a surprising fact, but when you have a linear transformation, now keep in mind, we know a lot of stuff about linear transformations. One of them is every linear transformation can be represented with a matrix. Right? Turns out that if you take that linear transformation and if you compute the derivative matrix of that linear transformation, it's always the exact same matrix, as it turns out. This is not hard to confirm. This is an excellent little exercise, again, that y'all can do. I encourage you to just do this for, let's say for 3x3 matrices. I think that's sufficiently persuasive. You don't need to get rigorous about it. But just take a 3x3 matrix, A, B, C, D, E, F, G, H, I, something like that. Right? Write down the linear transformation. Compute its derivative. Note that it is that same matrix, right? This is a plug and chug, easy, no tricky curves. Just plug in and confirm that this actually works out. A very nice fact to be aware of, though. Okay, so with that in mind, here's the example I want to entertain. We're going to look at this parallelepiped we're going to try to do an integral on that parallelepiped. So that's going to be our domain for a triple integral. Now, why are we doing this triple integral? I don't know, whatever, who cares? Some application, this is what we ended up with. I just want to entertain how would I rewrite this as an iterated integral and then compute accordingly. Okay. Let's take a moment to recognize what a nightmare this is. If you did this the old-fashioned way, if you sliced dx, dy, dz, anything along those lines, well, this parallelepiped has 8 corners, one of which is the start, one of which is the end. That means you're slicing through 6 corners. That means this is 7 separate iterated integrals. But it's worse than that, because some of those cross-sections, well, let me say it differently. None of those cross-sections are rectangles. Some of them are parallelograms. Some of them are triangles. Some of them are hexagons. Believe it or not. It's creepy, but it's true. Right? So each one of those, you're going to have to slice up as several pieces. Right? So this is far more than just 7 separate triple iterated integrals. This is probably more like 20 or 25. I don't know. It's a lot. So, bummer. We don't want to have to do that. Practically intractable. So here's the much better approach. And by the way, this is a tricky move. This is one of those moves where, again, you just have to see it once and then remember the trick so that you know next time you see it what that trick is. Here is the trick. Whatever these edge vectors are, the edge vectors that define your parallelepiped, make those the columns of a matrix. Let that matrix define a linear transformation. Let that linear transformation be your change of variables function. That's the trick. So again, this is not obvious. This is very, very, very not obvious. But if you follow this very not obvious trick, everything falls into place. And let me show you how lovely everything falls into place. So I claim, and I will justify this momentarily, I claim that my pullback domain is just the unit cube in UVW world. Just the unit cube. How do I know that's the case? Let's think about the edge vectors of the unit cube. The edge vectors of the unit cube, for example, I have E1 here. That's the first edge vector. Where does that edge vector go to? What's its image over here in XYZ world? Well, that's an input vector. It's going to go right in there. I'm going to compute by way of my function here. That is, of course, my change of variables function. How would I compute? Well, it says right here, if I want to know the image of that input vector u, I've got to multiply the matrix times u. Okay, wait a second. I've got to multiply the matrix times E1. Flashbacks to linear algebra. Matrix times a standard basis vector gives you a column. Right? And, well, let's see here. first standard basis vector means I'm going to get the first column, which, of course, as I cleverly arranged, is my first edge vector over here. So, wonderful little punchline. Each one of these standard basis vector edges of my pullback domain has as its image the corresponding edge vector for my original parallelepiped. And then you can make a linearity argument if you want to fill in all the details. But I think this is pretty persuasive that the image of this unit cube is my nasty parallelepiped. So, super cool. Neato. So we're in business. We have a change of variables function. We have a pullback domain, and it's all over with the shouting and some details. Z, we got to figure out what to do with that. I'll talk about that in a moment. We are going to have to compute our Jacobian determinant here. Our Jacobian determinant, keeping in mind that we're talking about a linear transformation. For a linear transformation, your Jacobian determinant is the same matrix. So that's awesome, right? So all I have to do is just take the determinant of this matrix. That's pretty straightforward, right? And so the last little detail is to figure out what Z is. My bounds, of course, are a freebie. My bounds here are the unit cube, 0 to 1, 0 to 1, 0 to 1. Can't beat that. So what is Z? And this is the last little bit. Just keep in mind that Z is the third coordinate of my output. Right? My outputs. Oh gosh, I think I messed up my colors. Let me do this in different color. It's the third coordinate of my outputs. My outputs are the x vector, x, y, z. Again, z being the third coordinate of x, y, z. So I just need to compute the third coordinate then of that product. So just multiply it out. We've got the A matrix. We've got that our input vectors here are UVW. And if you just multiply that out, pick the third coordinate, you will find that what you get is this. And I'm sure you've probably already noticed the 0, the 1, and the 5 happen to be exactly that row. Details are an excellent little exercise. Do make sure that you can do that. As always, if you get stuck for whatever reason, come to my office hours. I'll be very happy to help. Right? But I do think it's a good exercise to try on your own. Okay, yeah.
Yes, sorry for cutting you off, but I just need to explain again how we get this Z.
Well, okay, yeah. So Z is the third coordinate of the output.
Yeah.
The output is this formula. A is right here. Right? So just multiply it out. Multiply it out, and what you'll get, the third coordinate will end up being that.
Okay.
Yeah.
Thank you.
Yeah. Okay. Okay. So, moving along. We're still in section 5.5, believe it or not. Right? So it's this monster, gigantic section. It's enormous. It does make sense in a certain manner of speaking, because what we're about to see in some level is going to seem very different from what we've been doing, but ultimately it is in fact a change of variables. And I think that's the right way to think about it, is to think of it as a change of variables. So anyway, here we go. We continue. Recall polar coordinates. Y'all remember polar coordinates way back when? Chapter 1, I guess. And you can think of it as geometry in the xy plane, but you can also think of it as being a function. And I think this is a really nice way to think about it. It's a function that allows you to convert r and theta into x and y. And from this, you can make certain geometric interpretations about angles and kind of distances, but not really. They're actually coordinates, and it could be all of that's wrapped up inside of these functions, right? So I think it's easiest to just think of polar coordinates as being this function. Okay. All right. Well, here's the thing. That function got all the earmarks of a change of variables function. Two-dimensional domain, two-dimensional target. I can talk about how do I pull back. We'll get into those details in a minute. But I can pull back through such a function and take a domain here and turn it into a domain there. We can totally do change of variables with this. And in order to do so, we're going to need a stretching factor. Plug and chug. Y'all can totally do this. Make sure you can do this. The punchline is that stretching, well, this Jacobian determinant, not technically a stretching factor, got to worry about the absolute values, but that Jacobian determinant is just R. So again, calculation, ... means work it out, right? And you take these functions, you put it into there, you yada, 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 and that's what you're going to get. So it's a nice exercise. Everybody should do this once in their lives. It's your turn. Give it a shot. Okay, now here's the problem. As we just noticed, that is not my stretching factor. My stretching factor is the absolute value of that. Inconvenient and annoying, but really important, right? And true. So my stretching factor is, I'm going to have to figure out what to do with that absolute values, right? Nobody wants absolute values in their integrals. None of our shortcut formulas from single variable calculus will work with absolute values in your integrals, right? So this is unacceptable, practically speaking. Okay, so here's the big idea. We're going to work around this by the following choice. I emphasize this is a choice. There is no law that says we have to do this. We're doing this because we want to, because it's going to help us. But it's on our terms. We're choosing to do this. We choose to make the promise that we will always only allow R to be non-negative. No negative R's. So we're going to steer clear of what you might call the left side of the R theta plane. And when you make that promise, okay, well, R is never negative, then the absolute value dissolves. Right? No need to talk about the absolute value if you're talking about something that's already positive. Yep.
Doesn't that kind of severely limit us if we're only dealing with quadrant 1?
Yeah, I hear you. Yeah. So there is a case to be made there, but so do keep in mind that whatever points you're interested in the XY plane, you always have multiple ways that you can represent them in polar coordinates. And in fact, every point in the XY plane can be achieved with positive R's. And so all we're really doing is promising to make specifically that choice. But we will always have that choice. Was that satisfying?
Yeah.
All right. Okay, so good deal. Example to follow. While we're here, just for analogy purposes, let's go ahead and observe you can do the exact same thing to cylindrical. It's not quite exact, but it's really close to exactly the same thing. You can view cylindrical coordinates as being a function. You can compute the stretching factor. Yada, yada, yada. Good exercise everyone should do once in their lives. It's your turn. Give that a try. Turns out the answer is R. Keeping in mind that that's not the stretching factor quite. We do have to worry about the absolute values. Isn't that annoying? Okay, we'll make the same promise to always choose positive, non-negative R's. And then the absolute values goes away. And again, just R. Yeah? It's really, really similar how analogously that worked out. Okay. All right. And by the way, while we're at it, let's do spherical. Now, things are different with spherical. There's an important difference. Yes, we can still view it as being a function. Yes, we can talk about the Jacobian determinant. Yes, this is a calculation that everyone should do once in their lives, and it's your turn. It's not that convenient. This one's more like a 5-minute calculation, but it is a healthy exercise. I want everybody to give it a shot for whatever it's worth. This is not a, don't overinterpret from the following, but I did make this an exam question one time, whatever that's worth. And this is what you get. And now you're going to notice right there, that is not particularly analogous to polar coordinates. That's not R. That's not even kind of like R. That's really different. Right? So the analogy breaks down pretty quickly. Okay, so here we go again. I've got a Jacobian determinant of which I've got to take the absolute value in order to get the stretching factor, which I'm going to have to put inside of some integrals, and I hate having to put absolute values inside of integrals. Oh my gosh, how can I get around this bother? Right? Same kind of analogous situation, very different punchline as to how to do it. A lot of people think, well, rho is kind of like R. Let's just require rho to be positive. Does that help us? Not even a little bit. The problem has nothing to do with rho. In fact, rho can be as negative as it wants. Don't care. It's going to get squared anyway in this expression. Rho is not a problem. The problem is the sine phi. All right, this is what I'm worried about. This is what's going to make my potential absolute value nightmare. What promise can I promise that will allow me to state with confidence that sine phi will always be positive and that therefore I get to ignore the absolute values? And the way I can make that happen is by choosing phi to be between 0 and pi. It's got nothing to do with rho. Yep.
So do you suggest that we just memorize this?
Oh gosh, yes. Oh yeah. No, unless you just like going through tedious trigonometry calculations. Yeah. No, for sure. Absolutely memorize all of that. Yeah. Well, correction. Memorize this one little expression.
Okay.
Yeah. And then memorize would be the wrong word, but just don't forget the promise that we have to make the absolute values go away. Is that cool?
Yeah.
Okay, here's the good news. These are our favorite values of phi anyway, right? We always think of phi, angle off of the z-axis, as being between 0 and pi. Those are the easy ones, right? It gets real weird when you have a negative value of phi or a too big of a value. That's when we get all turned around and confused, and nobody likes that anyway. So if you promise to do what you wanted to do anyway, then you get the additional benefit of also getting to leave the absolute values that you wanted to do anyway. Total win-win. Is that cool? Yeah. All right. Okay, let's do one. I'm going to start with polar. Okay, so let's see here. We have the domain is this first quadrant portion of the unit disk domain for some integral. Why are we computing that integral? Doesn't matter. Some application. Let's just figure out how to do it. It's going to be a nightmare. If you come at this, sort of brute force, if you do this the old-fashioned way, these are what your bounds end up being. If you, for example, do it dy dx, it's equally ugly if you do it dx dy. Good thing to check. And you can see how bad this is going to get. Look at this inside integral. We're going to have odd powers of y after we do the dy integral. That means we're going to have odd powers of this square root. That means that our outside integrand is going to have square roots and worse in it. I don't think we want to do that. Right? All else being equal, we could possibly avoid it. This is not our favorite integral. Okay. All right. Okay. Well, here's the thing. Now I'm going to make a claim that I will back up in a moment. I claim that if I use the usual polar coordinates function, again, r and theta are the inputs, x and y are the outputs. With our usual formula, I claim that the pullback domain here is this rectangle. And we love rectangles. By the way, let's just see how enticing this is before we get into the details. We like rectangles because they have easy bounds. Easy bounds make for easy integrals. You can see this is going to be really, really nice. Right? We'll talk about the details in a second. Everybody see how again, the allure here? Everybody intrigued? Okay. All right, so now I got to justify for you, though, how do I know that this is the pullback domain? And, well, let's take it one edge at a time. Let me look at that edge right there. What can I say about this edge? Well, this whole edge is on theta equals 0. R starts at 0, R ends at 1. Okay, now keep that in mind. Theta equals 0, R goes from 0 to 1. In the xy plane, what do you get if you stay on theta equals 0 and go from R equals 0 to R equals 1? Well, you get that. Continuing. That next edge is on R equals 1, and theta goes from 0 to pi over 2. Okay. In the xy plane, where is R equals 1 and theta going from 0 to pi over 2? Well, it's that. Etc. That is this. And the weird one, this entire back, left edge here, that entire left edge is where R equals 0, which the whole thing kind of pinches down into a single point. And the way I like to think about this is just my own personal thing. I like to think of this rectangle as you pinch this entire edge down to just the origin. That kind of makes it kind of unfold like a fan. Kind of. Anyway. So, everybody buy it? Right, that the image of this rectangle is going to be this undesirable domain that we're dealing with. Yeah.
Sorry, could you please repeat the ones that were
Yeah. So this whole edge is on the theta axis, which is where R equals 0. Well, any point with R equals 0 it's the origin. Yeah. Right. Alrighty. So we are actually kind of in good shape now. We know what our pullback domain is. Our pullback domain is this, which therefore has these bounds. Don't forget, we've got to convert our sort of given integrand, plug in the conversion formulas. In other words, just remember how polar coordinates works. We already established long ago that x squared plus y squared is r squared. Don't forget your stretching factor. Our dx dy, as it were, is stretching factor times dr d theta. Again, we've previously discussed that the stretching factor is r. So we plug that in. Having memorized that from the previous page, and again, as somebody asked, yes, you should absolutely memorize it. It's super handy, comes up all the time. Don't want to have to redo that calculation every time. And we're in business. Everybody all right? All right, so here's question.
Wait, which one did you say to memorize again?
Oh, the formula for the stretching factor, which is in polar coordinates, it's just r. Yeah. So what I've done here is I have done a change of variables pullback using coordinate conversion formulas as a change of variables function. This is fine. This will handle anything that you need to do. But there is a much more efficient version of this. Right? And let's look at the efficient version. Let's try to figure out how to make our lives easier. The big idea, I'm just going to use what I have here. Let's look at our theta bounds. Our theta bounds were 0 to pi over 2. And because, there's my first theta slice, which is where theta equals 0, and then there's continual additional slices, and then here's my last theta slice, which I see is where theta is pi over 2. So my bounds 0 to pi over 2. Right, fine. Well, here's the thing. These theta slices, as I move along, those theta slices, I can just see what they look like in the xy plane. I don't have to literally visualize these slices perpendicular to the theta axis, they all represent constant value of theta. A constant value of theta is always a ray coming out of the origin. I can just visualize theta slices right there in the xy plane, looking at my original domain that I was given. I don't have to reverse engineer or figure out what is my pullback domain and slice that up. I can just do what I know theta slices are going to look like right here on the domain that I was given. It's a really nice little streamlining little idea. So let's do that. And by the way, this is just sort of the general observation there that, look, theta slices represent constant values of theta, and that's what constant values of theta look like. So let's do the same example again. Yes, it is a change of variables. Yes, there is a pullback domain. Yes, I could visualize slicing that up, but I'm not going to. All right? We're gonna remember that all of that is in fact underlying what we're about to do. But everything I need to determine, everything I need to learn from what I just crossed out, I can learn looking at this right here. Okay, so let's go through the process again. Here's our domain, right? Our domain is this quarter disk for this particular example, and let's. We know we're gonna do this with polar coordinates as a change of variables function. We know that our stretching factor is r. That's old news. We know that the algebra of plugging in makes x squared plus y squared convert to r squared. I haven't needed to refer to what's over here at all yet, not even a little bit. And then the last thing I got to do is figure out my bounds. So now let's think about the bounds. Fine. Starting with my outside bounds, theta. This is what slices look like. Theta slices. And that's the first one. That first slice, I can see it right here. The value of theta for that first theta slice is 0. Boom. Now, okay, yeah, sure. Again, you can think it is that slice of this pullback domain, but you don't need to see this to be able to conclude what the value is. You can see that here instead, and we already have this picture, so why not just work with this picture? That's the big idea. Now let's look at the last value of theta as my slices continue, et cetera, et cetera. My very last theta slice is that one. There's my last theta slice. And again, I have, thankfully, good sort of geometric intuition for polar coordinates, right? Because we did a lot of stuff with polar coordinates way back when. And yeah, that's pi over 2. And so, boom. We don't need to draw or even visualize the pullback domain that we're actually working with, because everything we need to know we can see in our original given domain. Okay, yeah.
Yeah, so this only applies to like polar coordinates.
Yeah, this is specific to polar coordinates. Yeah.
So
That's
continuing we had to because
one more time.
but when we're using the contingent coordinates, we had to look at the pullback, the one that we not correct.
Yeah, yes, everything that we're doing here is specific to polar coordinates only. Yep. All right. Okay, now let's, as before, now again, real quick, just as a reminder, where do we get the R bounds from? Well, we fix a value of theta, and then we look at, okay, well, where does theta start? And then where does R start? And then where does R end? Okay, so we're going to have to play that game. But again, let's do that without looking at that picture at all. Here's what a theta slice looks like. That's an arbitrary value of theta. And let's see here. Let's see, where does R start? R starts there. I don't need to pull back domain to look at that point and realize that being as it is at the origin, that is a point where r equals 0. And so we start at r equals 0. And where do we end? Well, we end at that point, which is on that curve, which has that equation. So my ending value of r is 1. So we see everything we need is right here in the existing picture, right? So just from a terminology point of view, what are we actually doing here? We are actually doing a pullback with change of variables, 100%. None of that has changed. But when we take this point of view where we say, look, I can just see everything that I need to see from there, this is casually referred to as doing the integral in polar coordinates. That's just language. In polar coordinates is shorthand slang for pulling back through the polar coordinates conversion formulas as change of variables functions. Everybody happy with that? Cool. Well, what follows? Just a bunch of examples. I'm going to hit the highlights of what I think are the most important aspects of these examples, and a bunch of what we're going to be seeing, or a bunch of what is on the page anyway, is stuff that's exactly analogous to stuff we've already done, and I'm going to gloss over and leave a lot of that for y'all to read. But let's look at this example here where my domain is the unit disk, and when you have what you might say, your region is such that your slices, as you're doing your theta slices, if you in fact go all the way around like this, and you can see those slices go all the way around right back to where you started, just don't forget that even though your starting direction and your ending direction are the same direction, yeah, sure, they are the same direction, right? But theta has increased by 2 pi in the process of going around, right? So even though you start by thinking of theta as being 0, when you end, after going all the way around, you have to interpret that ending as actually being 2 pi. So it's a nice little shortcut to remember. If your slices go all the way around, theta goes from 0 to 2 pi. Very convenient little punchline. So anyway, make sure to remember that little trick. Very useful. And by the way, again, yada, 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 a bunch of details. Make sure you can do all that stuff. I'm going to emphasize, don't forget your stretching factor. That's really easy to forget. It's really important. I'll talk more about that in a moment. Yeah.
What is the results tell us?
What is the what now?
What is the meaning of the results?
Oh, this right here?
Yeah.
Oh, that just tells us how to compute the integral that we were asked. And so, again, keep in mind that the reason we compute double integrals is because of lots and lots of different applications. And I could have made up an application here and talked about how, okay, well, the way we answer that application is to write down the following double integral and then proceed with this. But the point of this is not applications. The point is how to compute integrals, and integrals relate to applications.
Okay.
So I just want to focus on, you remember how we had that strategic diagram that has phase 1, phase 2, phase 3?
Yeah.
Right? So we're just focusing on phase 2 and phase 3.
Okay.
Yeah.
So we don't have to-
Yeah, so there's some application, whatever, some double integral. Yeah, right.
Okay.
Yeah. All right. Now, before we do another example, there are some little tips and tricks. I think these are really useful. I hope you'll find these useful. I'm going to say, let me say it wrong first, and then I'll correct myself. Just always do it in this order. Always dr d theta. Don't ever do d theta dr. There's basically never any reason that gives you an advantage if you do d theta dr. Right? So there's something really nice about the consistency of always doing it in exactly the same order. You'll always be looking first at theta slices, and so you've always got kind of the same sort of process. Now, minor correction. There are some examples where it is actually beneficial to do it in the other order. And those examples that I've ever seen in my life are all highly manufactured and unnatural. And I don't think you're ever going to run across one in the wild. So there's basically no cost. Just always do DRD theta. Okay. All right. Next. A very common story. I see this a lot. And this is a strategic point, not a mathematical point. It's very common for students to realize that they want to do polar coordinates, to write down DRD theta in recognition that they're doing polar coordinates, and then to realize, oh my gosh, there's so many questions about the slicing and the values and the angles and the blah blah and worrying about all of this stuff. And then having done that, they take this and they put it there and they go about the rest of the calculation and they forgot to put in the stretching factor. Now, I've seen it a million times. Right? I mean, when I first started teaching multivariable calculus, I would say about a fourth of the students would just straight up forget to put the stretching factor in there. And let's see how to say that. I totally understand how you could forget, because there's a lot of stuff to think about with the slicing and the bounds and the conversion. It's easy to forget. You don't want that to be you. Because this stretching factor that we just forgot here, right, is a really big deal. If you really think about it, this is the most sophisticated part of what we're doing. This is the multivariable calculus. Everything else is geometry and algebra. The multivariable calculus comes from how we think about the areas getting stretched. It's the most important single character in this whole thing, right? I have had exam questions, 20-point exam questions, where merely remembering to correctly indicate the stretching factor in the integral as being r can be worth up to 3 to 5 points for that one thing. I've had students who, 20-point question, and they leave a almost entirely blank page because they ran out of time, or they don't know how to do it, or I don't know what them. But anyway, for whatever reason, all they wrote was RD theta, and they get like 4 points. Right? So that R is bonkers important. Bonkers important. Don't forget it. And I think a really good way to not forget it, this is my personal ritual, I always write down R as part of this that I write down all at once. I don't ever allow, this is the plan anyway. I do my best, right? I'm fallible, of course. I try never to write down DRD theta by itself. Always write down RD theta together, and then you can't forget it. Does that make sense? And this is just a strategic point, right? It's just that you don't want to accidentally leave 4 points on the table that you could have had for writing a single character, right? It's too good to leave any chances. Okay. Lastly, this point right here, this is we've made this point a million times. If you want to know what your bounds are, right, recognize each bound comes from a particular point. Identify the point. Notice that point is going to be on a certain curve. Identify that curve. That curve is going to have an equation. Write down that equation, and then in that equation, solve for the bound that you want. Okay. All right, and let's see, how are we doing? We're probably out of time by now here. We're close. Let's see, I'm sorry. Yeah. I'm sure I owe you a minute, and we wouldn't be able to get very far into this next example. So we'll draw the line right there. Picking up here on Friday. Y'all have a good rest of your day. Don't forget about attendance if I didn't already get you.